the templates are on GitHub.
So once you click on the template, you push it to GitHub, and that's all we need to do for it?
Pretty much. Go to the GitHub, it gets your account on GitHub, and from Git, I'm happy to go over the procedure right now. Yeah, but once you click on GitHub, it's, I just don't remember if, depending how you are connecting to GitHub. If you're connecting to GitHub via the web, it will lead you to the template, and then you click download. If you are using if you're using one of the apps, you can synchronize it. The easiest is just use your web.
And once we're done, we push it to GitHub, and you can find it from GitHub, or how do we turn it in?
The whole story about create an account on GitHub, and then exactly the opposite story that I'm happy to demonstrate. That let's see. I'm very happy to demonstrate, but once you have it on your file directory, and then it's a story of sync, commit versus connect, commit, and update. It's just multiple steps stories, so it will be easier for me to demonstrate, or to have a 5 minutes video demonstrate it.
And then the conceptual questions we upload to Gridscope?
Yes.
Thank you.
And like people that took my stuff in other courses know essentially how create your homework in any way you want. That is, it needs to be a PDF, and it needs to be easy to read. But if you're using handwriting or LaTeX or Word, Google document, all acceptable. Just get one PDF to submit, or some combination of the above.
Thank you.
Yeah. Okay, so convolutions are confusing. And the good news is probably that if you are surviving this week, next meeting, the rest of the course, I think, is easier. I think. At least less confusing, definitely. So I have my kernel now would be a 10th function, and actually this interpolation that I do doesn't follow convolution exactly. I want to ask, that's where the red point is, I want to ask at the point that at the x, that's why it's not in the t domain nor in the spatial domain. I want to ask what is the value at x. And for to compute the interpolated value of the new function at x, I put the 10th around. That's what I do when I move the 10th left and right. When I put the 10th at x equal 4, then what I'm telling you is that I want to ask what is the value of the new function at 4. Again, I want to ask what is the value of the new function at 4, or the value of the pixel of the new image at 4. How do I compute it? In general, you'll think about, I want the average of this pixel and its neighbor from the left, its neighbor from the right. That's in the discrete part, right? Take the pixel, add to it the value of the pixel from the right, the value of the pixel from the left, sum it up, divide by 3. Voila, you're done. That's the average. The 10th kind of catches the same thing, except that here I'm willing to consider more than one neighbors from the left and the right, possibly a lot of neighbors. It's more of the continuous domains. And I want to compute my function at continuous domains. Like I can put the 10th at any point. What does the 10th says? It says that if I want to compute the value of my new function, again, the new point represents the new function. If I want to compute the new function at this x. This b is one of the data points. Ask at the x value of x, if the tent stands right here, how much weight do I give to b? Well, depending how far I am from where I want to compute. Remote neighbors are less influential than nearby neighbors. If I would have considered it only in the continuous domains, and I'll tell you in a moment why you need to care about these continuous domains, even though everything that you are doing is discrete. But if I want to ask what is a new or smoothed value at x0, here is x0, say x0 equals 17. What do I do? I'll look at x0 in discrete place. I'll say here is 17, 16, 15, 18, 19. Here are the values of y at 15, or the y values. So there is some function or data points that defines either in the discrete, or I try to guess what is this function. And now I sampled this function. I sampled this function at each one of the points. I want to ask in 17, so I'll check the function at 17, what's a pixel, what here at 17, and also what's a pixel value at 16, 15, 18, 19, and takes the average, or take some weighted average. Give this guy a weight of, give this guy a weight of 1/8, a weight of 1/4, half, 1/8, and 1/4. And obviously here I have a mistake because they don't sum up to 1. I want it to be a convex combination to make it to make it a smoothing. The smoothing should not be darker than the original image. So there is some bug here that the weights here don't sum up to 1. And everybody is good with this? I don't write it exactly because we had numerous slides on it. I want to know what the value at 17. Take the image value at the pixel you are on, the pixel that you want to know the answer. Add to it the values RGB of 2 pixels to the right, 2 pixels to the left, and take the average or the weighted average where the weights are considered, so that the further away you are, the less weight you're getting. I want to know what is the value at this point. Here is what's the height of the tent at this point. Tells me how much weight C is getting, the y value of C. How much weight the y value of B is getting. That's determined by the x at the tent. And of course, how much value, if I had the data point right here, then I will give a lot of weight for this data point. Why do you need to care about it? Why do we need to care about, why do I insist about this? Continuous domains also. And again, if you hide the convolution, it's not a huge part of the course. We'll pass it. It will take another 1 or 2 meetings when we'll talk about dynamic range and tone correction. And for most of the course, you can definitely survive with just interpolation. But so why do I want to think about a function with as a continuous function? Because let's think about the following. I'll give you an image of size 10 times 10. And I want to rescale it to 20 by 20. So here is my, let me make it a bit easier on me. In this example, I'll just show you part of it. I'll just show you 3 pixels. X equals 17, we like 17, 18, and y equals 3, and y equals 4. And you have an RGB value at each pixel. That's an input image. So since I scale it from 10 by 10 to 20 by 20, what should I do? This location of 17 and 17 and 4, it exists both in the old image and in the new image after the rescaling. So for each one of these pixels in the new image of the 20 by 20, I can take the corresponding old pixel that fits this location. And actually, you had the same question when you had the rotations. We'll see in a moment why when you did the rotation of the images, you could have accessed it if you want a nicer output with the approach that I'm presenting. So far I filled out, I think, half of the pixels of the output. I could fill it out in this way. What do I need to do to make it a 20 by 20 pixels? I mean, don't worry about the size of the image and how many centimeters it takes when I showed it on the screen. My question is, it's not we fail. I want to increase its resolution to present it as if it is 20 by 20. Help?
Use convolution. You can convolute it, interpolate it from the nearby points.
Exactly, but because what do I do? All these pixels, I can change their value, but all these pixels also appear at the output. Exactly in the same location. If we think about pixels as points, that is, this is the center of the pixel. The center of the pixel. If I want to draw the boundaries of the pixels, then the boundary of the pixels would create squares where this is the center of one of the pixels, and so is this guy. But right now I just drew for you the center of the pixels. That's fine for the 10 by 10. What happened in the 20 by 20? Where do I need to have more? I need to generate more data for the missing pixels. In the 20 by 20, there is a pixel but it didn't change. Put the mic on. class participation. Bump the grade of people that were in 70, they got numeric grade based on homework only and based on example. They got to 78 and they decided, you know, we're getting a B because you had fantastic class participation. You answered the question. The way you go. You came to office hours. That's I told you. It seems like you can. And so on and so forth for A and so forth for B and I don't think we can bounce to B. Okay. So, option one, I need to write something in this pixel. Option one, take the pixels from your lower left side. You want the connection. How would the image look like? We had these experiments many times of just scaling up an image where every pixel is just becoming 10 by 10 pixels with exactly the same value. Not great. Option two, which is kind of convolution, but not exactly. Formally, it's not convolution. What will make the picture looks a bit better? Absolutely sense when the new pixel is just at the center of the old pixel, which I can easily change in the rules if I change it from 20 by 20 to, let's make it 40 by 40. 40 by 40, you still have the old pixel. I deliberately put a number that is multiplication of them. You still have the old pixel, but now inside every old square, I have 3 by 3 new pixels that I need to decide about the values. I can do linear interpolation by taking these values. How can I do linear interpolation? By taking these 4 values, we take the value more when we talk about interpolation inside the triangle, we can use bicentric coordinates. Or we can decide that, you know, we want to know what is the value x, y, and to decide about the value of x, y, I want to give some weight to the values at each of the corners. How will I decide about the weights of these points? We'll talk about it more. Would be I draw a vertical line through the x-axis at this point. This determines the weight of the x. Similarly, I draw this determines the vertical of the x, and now I take the linear interpolation of these 2 points. Take the linear. I think that it was enough, so in this early stage, that's why. To interpolate. Xy. And then you go to upper one, P1. What are the P1, P2, P3, P4 over here? Oh. I'll just take this point. So I'll just zoom into this P1, P2, P3, and P4. What are I think about them both as points, L as a RGB value. The RGB at this point. P3 is with RGB at P3. Make sense? What are alpha 1, alpha 2, alpha 1, 1, alpha 2, 2? These are the weights that we give to each corner. Let's try to make it. Let's try to X, Y is one of the new pixels. And we need to decide what to Y for this pixel. And what I'm going to show you is a kind of linear, or to be precise, bilinear interpolation. Bilinear interpolation. P1, P2, P3, P4 could also be points in X, Y, Z, and then the same trick will give me a nice surface that I can now assemble for other part of the big surface and create a smooth and very friendly and not linear but bilinear surface that I can use to communicate with designers that suggest to move a few control points and the model, the shape of the new car will be determined by the location of these 4 points. How do I decide about what are these weights alpha ij? Let's draw the line. Let's draw a vertical line through the point xy. Xy, remember, it's the location of one of the new pixels. How did you get to it? Because you increase the resolution, or you did some translation, rotation of your old image. How do you generate properly the new image without missing pixels? You think about the location of each pixel, the location as a point, translate it into the input image. The location of the new point is somewhere between 4 existing pixels, and you need to decide, based on the location, what will be the value that you assign to this new point. So we are left with the problem of computing the weights of each point. It makes sense that if we are just in the middle, we give a weight of quarter to each one of the points, if we are just in the middle. And there are 4 points. And mind you, convex combination. Convex combination, the sum of the weights should sum up to 1, and each one of them should be positive. If it doesn't sum up to 1, then the new image will be brighter or darker than the original one. Okay, I'm computing D1, the distance. D1 will be the distance D1 will be the distance from the lower left corner to the X in the projection. So X is between X minus minus x of p1. So p1 would be x of would be x minus, let's call this point x0, y0 would be x0 x0 minus x of p1. What do I do with this? Essentially, I want to say if you're closer to p1 than you are to p2, then p1 should get more weight. And I mean this weight. And b then b2 would be, of course, x of p2 minus x0. x0 of this coordinate, which is also this coordinate. Even if the zoom is the font understood, not if the whole lecture. The font is readable. You have P1, you have P2. I will just copy out here is x0, here is P1, P2, and Z of P1 and Z of P2. If I'm just moving along this point, and I'm going to assign a color intensity value to this point x0 based on these two locations. We want a linear interpolation. How come v1 and v2 you're making sense? We want a linear interpolation that would be, in this case, w1 by potentially w1 and w2 such that p of x would be w1 p1 plus w2 p2. Now think about p1 and p2 on the color. It can also be the exact location in 3D, and then what you're generating is segments. So p of x 0 would be some weight of p1, some weight of p2, respect dependent x. And we want to make it reasonable and it's standing to think it's b1 divided by b1 plus b2. b1 plus b2 is just a distance from b1 to b2. And w1 is between 0 and 1. That's good. I'm always doing exactly the same mistake, but I'm looking at many times. What issue is that now if I'm very close to p1, or I expect p1 to be very aggressive, so and very little weight for p2, this number is it will be very close to 0. So I want to be very close to 1. So it's 1 minus this number. So it's actually b2 of the and w2 is of course 1 minus W. And then it makes sense because when x0 is at P1, all the weight is for P1. When x is at P2, all the weight, you're only taking a value on P2. And when you're somewhere in between, then you're getting linear interpolation. And actually, the stent that you see in the slide, that's exactly what it is doing. Let you write this line. Think about these points between C and B. When my tent, when I want to guess what is the value when I'm just on B, I put the tent just on B, and then all the weight is going to be on B. Zero weight to its neighbors, in this case. Well, the tent is at D2. All the weight is D2. And when the tent is somewhere in between, then the weight is linearly interpolated. And I still didn't tell you how to compute the values of alpha 1 and alpha 2, but they're almost there. And it's good that you ask because you might compute it in the homework, and because we have to cover it in the course on a very important part of the course. Small part, important. Similarly, so I computed B1, and now I have the value of W1 and W2. W1 and W2 I took from there. They are still not the alphas. Let's do a horizontal line. 2x0 y0, and here is D1 prime and D3 prime, and I want to interpolate the value at this point y0 right here based on what is D1 prime and D3 prime. D3 prime should be the weight over here. That is the interpolated value at P prime, the interpolated value at P prime should be some for weight W1 prime P1 plus W3 prime P3. P2 and P4 are not in the game because I'm just interpolating right now along this segment between P1 and P3. Exactly the same way that because I want to know what is the interpolated value right here, and similarly I want to know what is the interpolated value right here. So that's one way to think about it, and I will show you another way to think about it. Okay, what are these values? So maybe, what are they? W1 prime W1 prime would be just the same way, D3 prime divided by D1 prime plus D3 prime, which is 1 minus D1 minus D1 prime. So the weight of the weight that we assign to P1 here is D3 divided by the whole length. The distance on the opposite side. And W3 prime would be 1 minus W1 prime. willing to write what are alpha 1, 1, alpha 2, 2, and so on. What is alpha 1, 1? Four values. 1, 2, 3, 4. Each one of the, wait, now I have a point except what I showed is if the point that I want to interpolate, I have a new pixel that landed just on the edge, it connects to all pixels, just interpolate between the two of them. And if you have a new pixel that lies on the edge between two all pixels, again, just interpolate just this case. It's vertical, not horizontal. It's completely symmetric. But our issue is, of course, that I have new pixels that lies on neither of the edges, the interior one of the side. And in this case, I want to put in the game a chance to each one of the 4 points to express itself. But if the new point, the new pixel, x0, y0, is closer to one of the vertices, one of the corners, this corner should get more weight. And of course, alpha 1, 1, alpha 1, 2, alpha 2, 1, alpha 2, 2 are convex combination. Their sum equals 1, and they are all positive. So far, remember the old non-funny joke with a mathematician, you want to move it into a problem that you already solved. You can guess, almost. W11 would be, what did we say? This is, sorry, that's alpha 1, 1. Alpha 1, 1 say W1, W1, 5. And alpha was alpha 2, 1, alpha 2, 1 would be, what do we have? We are closer to that, so we are giving the weight over here, which is just the point. It would be W1, W3, 1. What about 4? With the weight alpha 2, 2, which would be, now we are measuring this distance and this distance and computing as the what would be alpha as W2 times W3, what? The weight to this one. What would be the sum of all these values? Think about it. You have 4 terms, but each pair of terms shares an element that is down, so easily to prove that it's a convex combination. Obviously, they are all positive. Let's see that it makes sense. First, what happens if xy is very close to P1? Then alpha 1, 1 is very close to 1, because product of 2 terms, both very close to 1. What happens with these terms if I'm on a point on one of the segments? If I'm on this segment, then the other segments get no weight. The point of the other segments gets 0 weight, possibly. So along every point on this segment, you're doing the linear interpolation between all the points. So that was one way to compute it. Another way to compute it will be, let's first declare the weight of this point. And how do I declare the weight of this point? I interpolate what happens on the bottom, just these 2 points. So decide linearly about the value of Q1, compute Q1 based on the 2 values of P1 and P2. Next. Decide what is the value at what is the value of Q2. How do I decide about the value of Q2? If I want linear interpolation, it's only determined by P3 and P4, and it's linear interpolation between them. Again, based on the distances, what was it? D1 and D2. It's a rectangle. What do I do next? Now I interpolate between Q2 and Q1. How? Linear interpolation once again. And you're getting to exactly the same formula. So I'll just write it down. I'll use this value at Q1 by interpolating P1 and P2. Compute Q2 by interpolating P3 and P4, and interpolate between Q1 and Q2 to determine what is the value at this point. Q is x0, y0. It has pluses and minuses compared to, it's much easier to explain the convolution. It's much easier to explain from convolution, but it has issues. It will not be necessarily, it will not be smooth. So it will be continuous, but between a lot of points, maybe you're careful. So when do you care about it? The very same trick will work if these are, let's say that I want to construct a visualization of a two-zone terrain. Look at the mountain. Look at the mountain. What are you getting? You're going to the geographic service, download the file, download it from other mapping services, which tells you what is the elevation on a grid. Put a grid on top of the mountains, or the mountains over here, put a grid above them. Here are my two mountains. Here is the grid. That's what the satellite or the airplane measured with the radar. That's what the input says. Basically every 30 meters or so. So to get the resolution, you have the elevation. points to tell me what is the mountain looks like between this data point and this data point. The elevation, how do you do it? That's linear, bilinear interpolation. Okay, so that's one way. Definitely you need to know in this course. What do I do with my tent over here? Here I wanted my tent, might be or not, but here I wanted my tent to actually create linear interpolation. You can do it, but then sometimes you can cover 2 points, sometimes you cover 3 points. You cover more points. How can I make sure that the sum of weights will always be 1? The weight against this point is where it crosses the tent, which happens to be at 1. But I also want to give some weight to the points to my right and left. Like so. Now I have 2 points, and I want the sum. What's the problem? If I always take the location where my tent for intersect the x value of the point, I just take these values. Well, sometimes it takes 2 points, sometimes 3, sometimes many. Like over here, sometimes many. And now when it's many, if I use the very same weight I used beforehand, just where it crosses the tent, and not do anything, then because there are many points, the value will be much, much higher. What should you do if you want to allow different number of points? In this summation, take the weights that are relevant, and take their sum, and always divide by each weight where I picked the x value, where I picked x value, take these values, sum them up, and divide the original sums. And then you don't care how many points you can cover. It will always sum up to 1. But it's not linear interpolation. It's not exactly convolution. But actually we will definitely use it when we talk about it's there also. Move to. We're almost done. So we will go back to the trick of taking the weights. That is it. Alpha I would be the alpha I prime, what I got from the value of the tent, divided by the sum of the alpha I prime of, let's call it live points. Live points. Points that the tent covers. So if you look at the code, you are, the sum is always 1. And sometimes we need this trick. You asked if it's more or less efficient. It's probably more efficient with linear interpolation, but how many neighbors do I pick when I compute this pixel? Only it's 4 neighbors. If you are happy with this, great. If you want to take more pixels around you, then you probably want to convolve with a tent or a box or a Gaussian that we'll not see in a moment, that we'll see next meeting. Yeah. if that's my only purpose, philosophically I can argue that the image might be, or mostly is continuous process, not necessarily constant, but might be continuous, and hence this pixel might have some error in it, but if I'll sample a bit from the side. But at the same coin, I'm also making the image a bit more blurry. So it's, you want less noises, less artifacts, then you're losing blurriness, unless you're, but there are tricks to prevent it. But yeah, so do I need more pixels? Yeah, and we'll see when we'll, many cases that I want to say it's Gaussian and theoretically everybody participates, just possibly with minusculous non-existing weight, or at least it's a tenth, so people far away will get less weight, but I agree, it's more resistance to outliers at the points, like maybe better reconstructing and more smoother if that's what you want, but realize that you are losing sharpness by doing so. And definitely there are better kernels and worse kernels, as we'll see. Okay, let's go through just 2 slides of this convolution. If I'm using box filters, that is box, I look at the 3 by 3 or 5 by 5 neighbors and just sum them up. And you might be able to see, or take the PDF, that the line, wait, why do I need to do this convolution? Because of more patterns over here. Because I use box function, give exactly the same way to all my neighbors. Even before the projecting, it looks very fuzzy. The brown strip is what used to be this brown strip is now all over the place, completely scratched. On the other hand, I can use Gaussian. It's not important, the statistic properties of the Gaussians are not relevant at this moment, why it's Gaussian. What is important is that it's friendly function that is easy to compute. The area, I can control it, the volume will be 1, so it's the correct number of weights, and it's just the further you're going away, the less and less weight there is over there. And without the theory just works very well for many processes. To use the kernel, which is Gaussian. And indeed, you might be able to notice that even I'll agree that if I take the original image, smooth it with a box, and it looks quite ugly, smooth it with a Gaussian, depending how centered the Gaussian is. Usually you take standard deviation between 1 and 3, and it looks both getting more. What are you getting by it? You're removing noise. If 1 pixel, because of the scanning property, 1 pixel decided that I want to be black, because I want to be white, because of errors that set it to 0 or 1, the smoothing will assign number that is nearby this value. Now, a trick that we'll talk about more in the next part is that sometimes I don't want to do smoothing uncontrollably in the last 30 seconds. So I want to generate a surface over here, and then I jumped to a surface over here, and this surface is rugged and there are noises, and I want to smooth it by doing the convolution. If I'll compute if I'll smooth it, taking the average, over here I'll get this line, over here I'll get this line, but now what happens in between? Put the tent or the box, try to guess what is the value right here, and the value right here will be somewhere in between, that's not such a big deal, but as the tent moves to the left and the right, you're generating something that used to be sharp and now is not, right? Because you're giving weights from here and here. If that's what you want, that's fine. If you don't want it, because now you completely missed that there are two surfaces with clear boundary in between, you're still looking at your tent, but you're saying, I'm only summing up points that are with y value, which is more or less the same. I'll have a threshold of noise that will say, for this point, I'm looking at neighbors of 5 by 5 neighbors around me, but out of all these possible points, I'm only sum up the ones that y value, elevation value, are close enough to the point over here. And other one I ignore. And in this case, you will smooth it into one straight line that gets over all the way up to this point without missing the boundary, and one straight line that gets all the way through here, and you will not get this washy path over there. But then you are summing up different number of points in each case. Sometimes it's 25 points, sometimes less. What should you do? Look at the points that you want to sum up, take the sums all together, and divide by the original weight. So as usual, it sums up to 1. And that works very well. And we will need it to get a high definition intensity that we are after. Thank you.
So for this problem here, which is the first, I think I showed you, I actually ended up coming across this and solving it myself, because when I was doing the rotation and the scaling, I said, oh, this pixel is coming from somewhere in this region, the nearest neighbors, it's not bad, but you know, it was visibly the problem with the
For
rotation.
homework one, it was allowable. For the next, it would be. Yeah.
For the problem with rotation is, and I did find a blog post that helped me come through why I continue to do it this way. But at first I was thinking like, well, it should be solvable that you have a new box that's like this. I mean, that's like this. But then all of a sudden now I need this pixel over here, maybe this pixel, because we have this rotated pixel is no longer in the same reference frame. And that makes sense.
And
Fix it.
in this way, the philosophical, or the way that I will try to describe it, and I think that in this way it's much easier, is to say that I have the old image. I have the old image, and the image behaves somewhat as a byte, in the zero before, while this is just a sample points that I do have, that's that I do have, that is taken from this region that I can only guesstimate. And so, you know, this is just a data quantity that I can only guesstimate. And now, but it refers to a pixels or objects or now the globus there. And now I'm going to sample the functions by doing the interpolation, guesstimation is guesstimating what happens to the original image in the whole region in between. And that's the whole image now comes generating the new image. The new image, and these are the center of the pixels. One of them happens over here. Let's guesstimate. But the reflection is doing this way. Yeah. The intersection of two square is here.
the weighted average, and that's what, that's how. And that's graphics, yes, in the same way. I always pick as a reader driver and the list of, I think in the Greek world, it's the pattern of the, and it's not a trade, it's a new pattern. If you're, in this way, I can say median one takes least sample checks, but the next thing is the next thing. So it will analyze it. And the same actually will be even if they did a line, there's a line where you compute the way the field based on how much of the area is inside the line. I can compute the area exactly in that part, but it's much easier to check for a few points randomly. Here it's not difficult. Check for a few points. Are they in or out? The field is much, much easier.
Thank you.
Thanks.